Welcome to the Rich Report, a podcast with news and information on the world of big data. Today, my guest is from Diablo Technologies. We have the VP of Marketing at the company, Kevin Wagner. Kevin, welcome to the show today.
Thank you. Great to be here.
Well, thanks for coming on, Kevin. I'm not really familiar with Diablo, so I thought we'd just jump into it and go into your slides and then do a Q&A at the end. Does that sound good?
That sounds great. All right. So if you have the slides up, let's go ahead and go to slide number 2, and I'll tell you about some of the highlights that the company has had recently, and I'll give you a little bit of background on the company, and then we can jump from there into what we're doing.
Terrific.
So we've created something called memory channel storage, which is a new system architecture for Flash, and that's what I'll be going through today and explaining to you what that architecture is and what it does for enterprise applications. Additionally, we closed a round of funding recently of $36 million, so we're a well-backed, financially speaking company. We developed a reference architecture called Tradeoff. Now, this is something that we developed to be able to validate and verify our design, as well as to use for software development and bring up purposes. Our approach in working with this technology is to work with industry leaders, work with OEMs and ISVs and end users in a very collaborative manner to make sure that the applications are very well tuned and very well suited for the technology that we've created. One of the important things here is that we feel that we have a pretty significant time to market advantage here, because we don't really see others doing what we're doing here. And our company has quite a bit of experience in DDR2, DDR3 memory interfaces and protocols, and we've been working on the memory channel for quite some time now. So this is an experience that I think gives us a competitive advantage in the market. Finally, we have a strategic partnership with Smart Storage. They are, as everybody knows, they are Flash experts, and they understand the enterprise SSD market extremely well. What they bring to the table is deep experience in Flash and in enterprise SSDs, and what we bring to the table is deep knowledge in memory channel interfaces and protocols. So it ends up being a very good, strong, symbiotic relationship with them. All right, then if you move forward to slide 3, we can start talking about the technology that we're building. Move to slide 4, and I will start telling you the advantages of the architecture. So first, let me explain this at a high level. What we're building is we are building a Flash-based product that goes on the memory channel of the system. And that will accelerate applications, and it will allow Flash to be used as a disruptive system alternative to both PCIe-based SSDs and to DRAM. And I'll go into some detail later on how we are creating that tier and disrupting the system. So to get into some specifics here, what we're doing is adding 200 gig to 6.4 plus terabytes of Flash placed into the industry standard DIMM form factor and on the DDR3 CPU interface. So effectively what we've done is we have taken the industry standard DIMM form factor, and we have created a module that has the same dimensions as a standard DIMM, that has the same pinouts and electricals as a standard DIMM, which means that you can literally take this and drop this into any of the DIMM slots in a system. The only restriction is that there be a DRAM module somewhere in the system. Any other slot in the system can be filled with this architecture. So one of the things this does for us is it gives us completely disruptive low latency, and that's one of the key factors here is the very, very low latency. SSDs have gone the route of moving to the PCIe bus to try to get better bandwidth and to get lower latencies. And in some cases, they've been able to effectively do that. They see latencies of 25 to 28 microseconds if there's no software layer involved and you're writing directly to the PCIe SSD. But there ends up being a trade-off that as performance goes up and you increase your IOPS out of the device, then you're also increasing your latency. We don't have that issue. We're on the memory channel, and therefore our latency writing directly to our modules is 3 to 5 microseconds. So you can imagine that is orders of magnitude less in latency than even PCIe SSDs that are out there. But also what's interesting is that as we scale and increase the performance of these modules, our latency stays the same, and it remains flat and consistent at 3 to 5 microseconds. There's another point here that I'll go into a little bit later on, but that point is, we can be used as a standard storage device just like any other storage device out there, and will show up in your system as a D drive, E drive, or however the OS decides to map that drive. But in addition, we can also be used as a memory expansion device. In other words, we can take the memory that's addressable in the system, and we can effectively add on to that memory space and create a much bigger memory footprint inside of the server. The last point here is that because we're using the industry standard DIMM form factor, this means that we can go into virtually any system that has an open DIMM slot. And so what has happened in the past is PCIe SSDs have been a good solution for certain applications. It's been very difficult for them to go into blades, and it requires very custom designs to be created for blade systems, and that tends to lock the blade into that PCIe solution. If changes are made to the blade, then the PCIe solution needs to change in many cases as well. Because we are standard form factor DIMM, we can go onto blades exactly as is, no custom work needed to be done, and we work just by plugging it in.
A quick question on this, Kevin. So, you've got this range of storage that 200 gigabytes to 6.4 terabytes in the DIMM slots. So I assume that your cost per byte is much lower than that might be with traditional DIMMs.
If you're comparing to DRAM DIMMs, then absolutely. Yeah. I mean, this is pretty key here. We are effectively using flash, and so you're getting very, very high capacities here and very large footprints, and you're doing it at the cost of flash rather than DRAM. So, by the way, one point on that 6.4 plus terabytes, it's the real limit here is simply the number of DIMM slots that you have in a system. And so this is why it says 6.4 plus terabytes. We have some applications that are looking at putting 32 or more of these modules into a single system. And so, 32 modules would, if I do my math correctly, would put you at 12.8 terabytes in a single system. You can go above that if you want to. It's all dependent on the DIMM slots in the system.
And is the OS aware of this, or do you have to add a module? Or how does that work?
So this is pretty simple, actually. So there are no changes that are necessary for the operating system. There are no changes that are necessary for the applications. It is essentially plug and play as you would any other device. There is a driver associated with it that gets installed just like you would with any other device going into the system, and that device driver will handle interactions between the operating system and our device. So this is something that I was pointing to earlier, which is that there is a trade-off traditionally between write latency and price to performance. And so, IT admins have been faced with a choice here between going the route of PCIe drives, where they can get a lower write latency, and they will pay more for it, in terms of dollars per performance, or they can go the route of SATA and SAS drives, and that might help them economically, but what it poses to them is the problem of longer write latencies, and so they'll have to live with those much longer write latencies, and that's a trade-off that IT admins have had to deal with in the past. We break that effectively by providing extremely low write latencies, and our dollars per performance or dollars per KI ops is much lower than everybody else. And so we've really broken that model. This is the current architecture, and you can see that we have a PCIe SSD in here. You can see on the left-hand side we have basically the CPU complex, where you have the processors, you have the applications, and you have system memory. And those applications are running on those host processors and executing everything out of everything it can out of memory and keeping as much data in that memory as it can. But much of its data is kept, external to the CPU complex. It's either out on a PCIe SSD or, external storage arrays or some other type of storage device. To be able to get that data and bring it over into the CPU, if you press the button and build it out, you can see that the data has to move from the PCIe SSD through the I/O hub over to the processor and into system memory, and then back and forth. And so there's two problems here. One is that there's a pretty good distance between those, and so that's where the latencies really come in. And the second thing is that there ends up being quite a bit of contention on the PCIe bus and contention going through the I/O hub. And so that causes a couple of things. One is that causes lower performance as there's contention on the bus. And then the other thing is that causes, the higher latencies as things move back and forth between the storage and the CPU. If you go to slide 7, you can see what we're doing here. So if you build this out and push the down arrow, you can see that what we do is we put our modules into the memory space. The PCIe SSD goes away. If you push that again, then you can see we take the data that's needed by the applications, we move that over to our modules, and we now have all of that data right there in the CPU complex, easily accessible at very low latency and very high performance. So now everything you need for those applications to execute is effectively in that CPU complex. This is really where we get the great performance and the low latencies. Any questions on this so far?
I was going to ask you about, this is non-volatile memory, correct? I mean, it doesn't need energy to refresh?
Correct. So this is, this is flash memory behind our controller. So it's persistent memory. We do have power fail protection on these modules. And so, essentially, as soon as any data arrives on the module, we can persist that to memory and commit that. Even in the case of a power loss, we have enough power on the modules to make sure that anything that has arrived on those modules is then committed to persistent memory.
Kevin, I come from the HPC space, and they're always concerned about energy consumption for these, because they put as much memory in these things as they can. Have you guys looked at, does this consume less energy than filling up your slots with traditional DIMMs?
So it's going to be, fairly similar in energy in terms of, how much energy it draws per DIMM. However, you can look at it a couple of different ways. One is that you're getting much, much greater capacity, and so the capacity to power ratio is going to be very, very different here and much better. The other thing to consider is that, if you're putting these modules in and you're comparing it to the power that PCIe devices draw, there's also a big difference there. PCIe can tend to draw, very large amounts of power and require a lot of cooling, and so we end up looking very good compared to PCIe as well. All right, so if we want to move to slide 8, we can start talking a little bit about the architecture and applications and such. So this slide, you can see a few things happening here. So there's a few points to make here. The first one is that, I explained earlier that our modules can go into any of the DIMM slots in the system. And so we get a few benefits out of that. One is that each of the modules has a direct link to the processor and has its own memory controller. And what that means is that it ends up being extremely parallel. So if you look at other solutions that have to share buses, you end up with a lot of data contention, and you end up with a lot of latency associated with that. In our case, we're on the memory channel, and we're connected directly to the processors. The modules have their own direct links into the processors, which means that we end up being extremely parallel. So that does a couple of things for us. One is the parallelism gives us extremely scalable performance. And so if you look down at the right-hand side of the bottom chart, you can see that the read IOPS and the write IOPS scales extremely linearly as you add more modules into the system. So if you go from 2 modules to 4 modules, you're literally doubling your performance. If you go from 4 to 8, you are doubling it again. And that's something that you don't see with other buses. That's because we're really taking advantage of the highly parallel nature of the memory controllers and the processors. The second thing that we gain here is again the latency, because each module is directly connected to the processors and has its own connection directly to those processors. We get very, very low latencies. Now, if you think about NUMA architectures, this also means that it doesn't matter where in the system these modules are. We take advantage of the NUMA architecture and the QPI or hypertransport interconnects between processors, which means that wherever these modules are in the system, any core in the system can effectively access those modules, and you're not talking about adding latency to that at all because the NUMA architecture allows for that to happen. So you're literally talking about nanoseconds being added in terms of latency, which when it comes to storage is extremely low.
So Kevin, when I'm populating a system with memory, they always for maximum application performance, they always say put the same size DIMM on the same bank. So do you have that restriction, or do you get around that with this architecture?
So if you're talking about kind of how how our modules are added to the system, and are there restrictions on the capacities of those modules, and do they need to be all of the same capacity? The answer is no. You can mix and match these. You can put in a number of 200 gig modules. You can put a number of 400 gig modules. You can put them into any DIMM slots in the system, hanging off of any processors in the system. It doesn't matter where you put them, and it doesn't matter if you're using different capacity modules to put into the system. It's all handled seamlessly. Okay, so if we move to slide 10. Now, what you can see here are some use cases for our memory channel storage. It ends up being a very flexible, efficient architecture, and there are actually multiple ways that we can use this. So on the left-hand side of the screen, you can see that it says I/O acceleration. If you click and build that out, you can see the CPU and the applications connected to memory. Click that one more time, and you can see our modules slide into the memory channel. Click that one more time, and you'll see how it's being used in that case, which is as a traditional storage I/O device. So in this case, we're being used the same way that any other storage device would be used, except that we're much faster and we're much lower latency than other solutions. Now, if you click again and see the right-hand side start to build out, you can see something called application memory expansion. And you can see tens of gigabytes of memory in the system. If you click again, you can see that our modules slide in. Click one more time, and you can see that we've now changed from gigabytes of memory in the system to literally terabytes of memory in the system. Click one last time, and you'll see exactly what we're doing here, which is we're expanding memory from tens of gigabytes to terabytes. This essentially gives you terabytes of system memory that the applications and operating system can use. And essentially what we do is we do ultra-fast paging at near DRAM performance and latency. So you're getting very near DRAM performance and latency, but you're adding literally terabytes of memory into the system. Now, one of the questions that comes up is, so what do applications and operating systems have to do to be able to take advantage of that? And the answer is nothing. Our driver takes care of all of this, and so the operating system does not need to change to be able to use this feature. The applications don't need to change to be able to use this feature. And this is really something that's going to matter tremendously when it comes to applications that like to run everything in system memory. And so big data analytics, memcached implementations, any of these types of applications are really going to be able to make use of this expanded memory. So on slide 11, you can see we have this configured as a server or storage array cache. If you click the button, and you can see our modules slide into place, and then you can see the points build out on the right-hand side. Effectively, what we're doing in this case is we're using our modules as a flash caching solution. So if you pair our modules up with flash caching software that's out there, we can be used as a flash caching device for external storage arrays or for lower tiers of storage. So this works the same way that any other device out there would work. It shows up as a drive in the system, and so it can work with caching software just perfectly. Okay, if you go to slide 12, you can see the applications that we are targeting for this. The first one is financial services. In particular, we are targeting high-frequency trading initially, but there are other areas of financial services that can obviously take advantage of this as well. High-frequency trading is very prone to low latency systems and really likes to get the lowest latency possible for all of the trades that they're dealing with. I'll show you a slide in a moment that will show the benefits in high-frequency trading. The second area is database and cloud. So we see a very good use case for this for database and cloud type applications, memcached implementations, MySQL implementations. Those tend to be very good use cases for this, and we have partners that we've been working with, ISVs, that have been proving that out for us and have seen tremendous gains. The next area is virtualization, and I've broken this up into two different areas. One is server and storage virtualization. The second one is VDI, and there are certainly benefits in both of those areas of virtualization. And we've been working with the leading virtualization providers to prove that out. We have drivers that we have for hypervisors to make this work with those hypervisors, and we're seeing very, very good performance gains there. The final area is big data analytics. So you can imagine that big data analytics is a very good use case for this. Being able to move everything into system memory and run everything out of system memory ends up being extremely useful for a lot of the big data analytics guys. So on this slide, you can see an example of high-frequency trading or high-frequency messaging. So this is a company that it's an ISV that we've been working with that has created a messaging platform for high-frequency trading. And they've been working with PCIe SSDs, one company in particular, for about 5 years now. And they've been working with them to see the benefits of low latency flash. And what I said before was that typically you see 25 to 28 microsecond latency on PCIe SSDs. That's if you don't have any software involved. When you start adding the software layers, then obviously the latencies are going to be higher. And so this ISV ran their workloads. They did all of this testing, not us. And they ran their workloads on this. And what they see on PCIe is a range in latencies from about 150 microseconds up to 2 milliseconds. And it ends up being extremely variable, going on up to 2 milliseconds over time quite regularly. In our case, if you look down at the very bottom of that chart, you will see a red line that goes across, and that is the latencies that they saw in running their platform on our architecture. And what we saw was that we were down around the 60 to 70 microsecond latency range. But more importantly, actually, is the deterministic or the constant latency that you see. What ends up being difficult in high-frequency trading is that variability in latency. And so we have really been able to knock that latency down and keep it extremely deterministic for these guys. And it's caused quite a bit of excitement in the high-frequency trading area. So this is an example of a memcached implementation on Open Compute. Again, we have a data center, call them a data center ISV that we've worked with that has a memcached implementation. We had them do a study on what would happen if they move their memcached implementation over to using our architecture. So if you click on this slide, you can see the left-hand side build out. And you can see what they have been doing in the past is using 25,000 systems. They've been using all DRAM. And so what they do is they load their systems up with 144 gigabytes of DRAM in a single system for 25,000 systems. They then move to our architecture, and they are able to get the same work done in the same amount of time on their Memcached implementation. But in our case, they're using 5,000 systems. They're only using 16 gig of DRAM in the system, and then 800 gigabytes of combined storage from our modules. And in this case, they're using as memory expansion. We had them do a TCO analysis, and so they looked at the CapEx and the OpEx. On the CapEx side, obviously there's a lot of savings that are involved in going down from 25,000 systems down to 5,000 systems. That consolidation helps tremendously. But even bigger than that is each system going from 144 gigabytes of DRAM down to 16 gigabytes of DRAM plus our devices. That ends up being the biggest cost savings for them in terms of the CapEx. They also looked at the OpEx, and they did this over a 1-year period and took a look at what it would save them in energy and cooling costs for that 1 year. Now, certainly, if you went out further, they would save more in the second year and third year. OpEx would push out further, and they would save more in subsequent years. But they did it for a 1-year period, and what they calculated was a $31 million per year savings in that first year. Now, yeah, that's pretty exciting, and a lot of that is due to the CapEx reduction, but also a lot of that is due to the OpEx reduction. You can imagine that was quite exciting for these guys. As I said before, this is a company that is building very, very large data centers. So you can imagine that the consolidation for them is a huge factor in technology that they choose.
Yeah, I mean, with the 20,000 less systems to run and power and administer, that I just see huge savings.
Yeah, that was one thing that they didn't calculate into here was the administration of all of these systems, but that would certainly add on to the savings as well. Having 5,000 systems to administer instead of 25,000 is a very, very large difference. So this is an example where we are using these modules in a virtualized environment. And what you can see here is there are a few things going on. So first one is higher performance. And this is something that you see quite regularly in the virtualized world. You want to get more VMs running per physical host. And certainly we're able to do that, and we can show some great consolidation gains by using this solution. But additionally, we can also lower the cost. With a DRAM cost reduction of about 70% by putting less DRAM in there and using this solution, you're also going to get much lower cost. Another point here is the DRAM-like performance. So one of the challenges that you face in dealing with storage in virtualized environments is that the more virtual machines you add, the response time increases dramatically. And that's just something that people end up living with in a virtualized world. And you add more VMs and your response time, gets much worse. In our case, because we're on the memory channel, because we have such low latencies and we have the great parallelism, you don't see that behavior with the modules that we've designed. So as you add more virtual machines to the system, the response times and the servicing of those virtual machines stays very, very, very good. There's one other point on this slide that's kind of hidden, but it's a pretty important one, which is what you see there on the left-hand side is a series of blades. And so one of the things I think I said earlier was that this ends up being a very good solution for blades. One of the big reasons for us wanting to be able to build this architecture and to use standard DIMM form factors is so that we can take this architecture and place it directly onto blades without any changes. So no custom designs, no changes, it goes right into the DIMM slots, and it supports blades extremely easily. And that's true of anything. So, we can put these into storage arrays, we can put these into servers, we can put them onto blades. Anywhere that you can see a standard DIMM form factor, we can place these modules. So this is kind of our summary slide here, and kind of reiterates everything that I've said already, which is, we have effectively used the memory channel of the system to provide flash storage and memory expansion capabilities using a standard DIMM form factor and the standard DDR3 CPU interface. And as I said, what this provides is, very disruptive latency and very, very good performance that will help accelerate applications in the enterprise.
Well, terrific. So, Kevin, you haven't mentioned HPC as a use case. Have you been talking to folks from that community?
Yes, actually we have. So, I haven't listed that on here, and part of the reason for that is, what we want to do is we want to make sure that we approach each of these use cases very carefully, and we want to service them appropriately. So we've started with the use cases I listed earlier, but certainly we see a very, very good use case for this in HPC. There are a number of workloads and applications in HPC where we see this playing a very, very big role. There are a lot of areas of HPC where, very, very large data sets, being in memory is extremely beneficial and useful. They're using a lot of memory to be able to do that. A lot of the simulations are requiring, extreme amounts of memory, and certainly that's an area where we're going to play very, very well.
Terrific. This is really exciting. I guess my first question I thought of is, why hasn't someone thought of this before? Was there a technology hurdle you had to overcome to be able to deliver this?
That's a very good question. I think there's two answers to that. I've thought about this quite a bit, actually, and I think there's two answers to that. The first one is, to your point, there is a bit of a hurdle in being able to do this. This requires a lot of deep expertise and knowledge in memory controllers and DDR3 interfaces and protocols, and it's knowledge and experience that Diablo has, just because we've worked on that bus for the past decade, and so we've come to understand it very, very well, in ways that a lot of other companies really haven't. The second thing that I would say is that, I think traditional storage suppliers or traditional storage vendors, they tend to think of storage more as requiring storage protocols and traditional storage interfaces. And so when Flash, started making its way into the PC as storage, it was a natural thought to put it on the SATA and SAS controllers, and then when they wanted better throughput and lower latencies, it seemed very obvious to move that to the PCIe bus. In our case, because we come from the memory world and DDR world, it just seemed much more natural for us to take it and place it on the memory channel. I think if you play this forward, I think it'll be much more obvious to people going forward that this is where Flash really should belong, and this is where it really needs to be. I think it's just it was different thinking for them, and it wasn't different thinking for us.
Yeah, and you certainly have first adopter advantage here, Kevin. Is there anything stopping people from taking their SSDs and putting them into the DIMM factor once they look at how to do the memory interface, or you think it's going to take years for them to catch up?
I think that it will take quite a bit of work, quite a bit of experience and knowledge to be able to do that. Certainly we're always looking behind us to see who might be working on similar technologies. But I do think that we have something that is very, very unique and certainly isn't easily replicatable.
Yeah. Well, this has been fascinating, Kevin. And when is this going to roll out and be generally available?
So, if you don't mind, I will defer that question. And the reason being that
okay,
we're working with Smart Storage, and
problem.
they will be productizing this, and then the OEMs will be selling this in their systems. So we have a number of OEMs that are working on this, and they will announce at the time that they've gone through their complete qual cycle. So it's really dependent on,
Right.
on going through SMART and going through our OEMs.
Sure, sure. So are you licensing this like a patented technology? Is that how you're doing it?
So we're not licensing our technology out. We use the
Yeah.
technology to create a reference architecture and worked with our partner
Uh-huh.
to be able to create that. But we're not looking currently at licensing this technology out.
Well, Kevin Wagner, this is very, very fascinating, and it looks like the future is bright for Diablo in this space. But I want to thank you once again for coming on the show today.
Thank you so much for having us. We appreciate that.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of big data.